In this video, we're going to explore how to solve exponential equations algebraically. We know we're dealing with exponential equations when an exponent or an index or a power are involved. We're first going to consider equations where the unknown, the x in our case, is in the exponent or as a power. When we're dealing with situations like this, one of our options is to try and make all the terms involved in the left and right sides of that equal sign contain the same base value. In our first example, we have 2 to the power of x subtract 1 equals 8. Now we have a base of 2 involved, and I know that the value of 8 can be changed to 2 to the power of 3. So straight away I can make the change that the term on the left side and the term on the right side are both now written as a base of 2, which tells me that they should be equivalent. So the exponent on the left side and the exponent on the right side must be equivalent. Hence x take 1 must equal 3, therefore x equals 4. There is another way we can consider solving this question, and that's by breaking down that left-hand side. So rather than having 2 to the power of x subtract 1, we can break that down using our index law, saying 2 to the x and 2 to the negative 1 equals 8. This means 2 to the x over 2 equals 8, which means we can undo the divide by 2 by timesing by 2 on each side, which gives us 2 to the power of x equals 16. And we know that 16 can be written as 2 to the power of 4, so x is 4. So there is another approach we can take if we can see that happening, where we can use that index law to pull apart those two terms in the exponent. So let's consider part B. I'm going to try and make the bases be the same. I can see a 9 and a 27 involved. I'm going to rewrite these as a base of 3. But before that, I don't really like dealing with a fraction setup. So first of all, I'm going to rewrite the term on the left as 9 to the power of negative x equals 27, just so I'm dealing with everything as a numerator. I'm going to change 9 to 3 squared, and 27 is 3 to the power of 3. So I'm going to just use the power to a power law. So I've got 3 to the power of negative 2x is 3 to the power of 3. This tells me the negative 2x must be equal to 3. So if negative 2x equals 3, then x is negative 3 on 2. In part C, we've got a fraction, a quarter, to the power of 1 subtract x equaling 8. Now, I've got a numerator and denominator both to the same power. We know that 1 to the power of anything is just 1. And my denominator is also to the power of 1 subtract x. Now I'm going to use the negative index law to bring this up as a numerator. So I've got 4 to the power of x subtract 1, because the 1 has become a negative 1, the negative 1x become positive, and this equals 8. Now I know 4 and 8 can be written as a base of 2. So this is 2 to the power of 2 to the power of x take 1 equals 2 to the power of 3. So straight away I know that I can utilize these exponents. I've got 2x take 2, just using the power to a power law to expand that power out, equaling 3 on the right side. So 2x equals 5, therefore x equals 5 over 2, or 2.5 as a decimal. Now my last example, when the power is the unknown value, is when we have what we call more of a quadratic type setup. I'm going to start by looking at my 3 terms on the left and noticing that we do have a base of 2 and a base of 4. But I know a base of 4 can be written as a base of 2, so that's my first step. I've got 4 can be written as 2 squared, instead of just 4 to the power of x. Then what it makes me realise as I expand out this power to a power, I've got 2 to the power of 2x. Or in fact, if I wanted to swap them around, I've got 2 to the power of x squared. Subtract 6 to the power of 2x plus 8. This reminds me very much of a quadratic. If we let 2 to the power of x be represented by m, I could replace each 2 to the x with an m, simply saying m squared take 6m plus 8 equals 0. And straight away I can see that I could actually solve a really simple quadratic here by trying to factorize it into 2 brackets, and then I could go back and deal with my 2 to the power of x. So let me show you how this works. In factorizing into double brackets for a quadratic, what multiplies to give 8 but adds to give -6? We can spread out that m squared. Well, 4 times 2 is 8, and 4 and 2 does make 6, but I need -6. So I'm going to say that they both have to be negative. -4m, take another 2m is -6m, and -4 times -2 is +8. So now I've got some solutions. So let's go back to this first one that I can create a solution. Let's replace the m back with 2 to the power of x. So my first option for a solution is 2 to the power of x take 4 equals 0, which means 2 to the power of x equals 4. Now I know that 2 to the power of x is the same as 2 squared, so x could be 2. Or my other solution, replacing the m back to 2 to the power of x, take 2 equals 0. 2 to the power of x is 2. That's 2 to the power of 1. So x could also be 1. And I have 2 possible solutions in this situation when I solve this exponential. So when solving when the unknown is the exponent, the aim is to get the base numbers the same, so I can look for some equivalents on the left and right side. Let's consider now what would happen if the unknown is the base value instead. So here we have 4 examples. Starting with our first one, we have 2 times x to the power of 3 on 2 equals 16. Now if we were solving something as simple as 2 to the power of 2x equals 16, we would simply divide by 2 and have x is 8. And we're going to start with that step straight away. Remove any what we call coefficients. So by removing the coefficient of 2, I'm left with x to the power of 3 on 2 equals 8. Now we're going to use our power to a power index law, and we're going to break down this power of 3 on 2 into a half times 3. And I'm going to keep the half closest to the x to the power of 3 equals 8. So what we're now wanting to do is remove a power of 3. Now if we want to undo what is power of 3 or a cube, we would cube root. So if we think about that idea of going through and cube rooting both sides, the power of 3 would disappear. So we could cube root the left side and cube root the right side. One way I like to think of it, a cube root is just a power of 1/3. So what I like to consider is actually going through and multiplying through the power on the left side by 1/3, and there's a power of 1 on this 8, multiplying that by 1/3. Which means that that's going to cancel down to a power of 1, and we're left with x to a half. And 8 to the power of 1/3 is like the cube root of 8, which we know is 2. Now to undo a power of a half, this time we could put a power of 2 on, or square each side, power of 2, which means that we're going to have 2 times a half leaves x to the power of 1, which I don't have to write the power of 1, and 2 squared is 4. And we have our solution of x equals 4. So let's try this with part B. We've got x over 2 take 1. That whole expression is to the power of 3 equals 125. So straight away, I need to get rid of this power of 3 or this cube. So we could think about this as cube rooting everything on each side. Or another option of thinking about it is to put everything to the power of a third. Hopefully you can recall that the cube root of 125 is 5. And we're now releasing that bracket. X divided by 2 subtract 1 is free. So to get rid of the take 1, we can add 1 to both sides. And to get rid of the divide 2, we can times each side by 2. And we have a solution of x equaling 12. So in part C, we've got x cubed equals x squared. So what is a number that we can cube that is also a number that we can square that would give the same value? If we think about that logically, and we start inputting numbers for x, like 2 to the power of 3 is 8, and 2 to the power of 2, well, that's not going to work because 8 doesn't equal 4. What is the possible numbers that we can put in here? There are, in fact, 2 possible solutions in here. Let's consider one solution. To get rid of so many x's, we could divide each side by x squared. That would be very valid, which would leave x equals 1, our first solution. However, when we simply go and divide through by a number, we often miss another solution that does exist. So I want to think back to a previous example where we did the quadratic, where everything was put to the left side and equal to 0. So if we decided to take x squared from each side, we would end up with x cubed take x squared equals 0. And I had the idea to do this because x cubed and x squared obviously have common factor. They have a common factor of x squared, which makes it look a little bit like a quadratic, a binomial product. So in fact, we do have 2 solutions. We have the solution that x equals 1, but we also have the solution that x squared equals 0, so therefore x is also 0. So we can see that our approach to a question could either gain us 2 solutions or only reveal 1. So in our last example, we've got the square root of x equals 5 times x to the negative a half. So in this situation, once again, we can see that we've got x to the half equals 5 over x to the half, if you like. There's 2 options that we can take here. We could put it to a positive power and multiply through by x to the half to remove this x to the half, and this would look like so. To remove x, divide by x to the half, we would multiply each side by x to the half. That would leave us x to the power of 1 equals 5, and we have a beautiful solution. Another option we have is to consider dividing straight away by x to the negative a half. So we'd have the square root of x equals x to the negative a half equals 5. And thinking about our bases and our powers here, we've got x to the half divided by x to the negative a half. And our index law says when we're dividing with the same base, we would add the indices, which would give us x to the 1 equals 5. So whichever way we consider doing the manipulation to solve, we still arrive at our answer of x equaling 5. So now it's your turn to pause the video and have a go at the 5 solving questions that have been supplied to you on our worksheet. I'd like you to have a go at these, looking back at the examples that have been shown, and then come back and check your solutions.